Hi, everyone on this webinar. So I'll be taking you through a very brief introduction of electric drives. Uh, so let's have a look at what we have set up over the next 40 to 45 minutes. So we'll understand what is an electric drive, and we'll also look at why is it required? Why is an electric drive really necessary? We'll understand the evolution in terms of the technology improvements that have happened in electric drives. What are the common applications of electric drives? We'll also look at how is an electric drive built. That means how is it put together, various components, how they come together. We'll understand one case study from the aerospace domain, and then we will look at what are all the different aspects of electrical engineering and mechanical engineering, including even embedded software, firmware, how all these cross-functional fields come together in making an electric drive. And later we will go through what are the career opportunities that are one can make off in the electric drive, and finally, we'll end with some of the present challenges that are there in electric drives. So let's get started with what is an electric drive. Uh, so there are two elements to the answer to the question. So one part is the main key element of an electric drive is that we are basically controlling a motor so that the motor can actually drive some mechanical load or create a mechanical motion. So the electric drive, which is controlling the motor, the purpose that it exists is basically to convert electric power from a fixed form, which is available in most of the utilities at industries and homes, to an adjustable form. So basically, I'm converting some parameter, which is mostly the frequency, to an adjustable form. So you have typically, you might have heard of the term variable frequency drive. So that is the basic purpose of an electric drive. And the drive will be basically used to control the motor, which is driving a mechanical load or creating a mechanical movement. So just the electric drive is not alone sufficient to control the motor. So we have a set of components which are part of the overall electric drive system. So one of them, which is a key component, is what we call as a controller, which provides the command to the electric drive in order to control the speed of the motor or the position of the mechanical load. And that is basically the brains of the electric drive. And in addition, we have the heart of the electric drive, which is typically called the power processing unit or power electronics, which goes into the electric drive. So the controller is basically coupled or tied with the power electronics. And in addition, we also have a lot of sensors which enable the functioning of the drive. So all of this put together, like what we see here in this figure, form the electric drive. So if you look at the figure, what we see is we are getting a fixed form of electric power from the source, and that is basically conditioned by the power electronics or the power processing unit, which drives the motor. But in order to control the motor, you need a brain basically, which is the controller. The controller is taking feedback from the sensors, which are all connected to the motor and also sometimes to the load also. And the controller basically using all this information coming from the sensor and also any commands which can be provided. Uh, it basically drives or instructs the power processing unit or the power electronics on how to control the speed of the motor. So this is the very basic block diagram of the electric drive. So you can see in the legend, we are talking about the power flow and the signal flow there, which is highlighted in the figure. So the power flow is basically what is being provided to the motor through the power processing unit. And the signals are basically signals which are used from the sensing the mechanical load position, or it could be used to sense the motor speed. So these sensor signals are basically coupled to the controller. So this figure is important because as we go ahead, you can tie it to the different aspects that I'm going to talk about in terms of what are all the various cross-functional areas that are applicable to the development of an electric drive. So as we go ahead, you will understand how they all come together. So now, when we touch the evolution of the electric drive, um, the one basic question that gets answered is why do we need an electric drive? So as I mentioned earlier, motors are going to be used to drive the mechanical load, but the power that we get from the utility grid is in a fixed form, and that does not allow us to run the motor at whatever desired speeds we have, or basically it is a need for adjustable speed. And this is driven because various industries where the more electric drives get used, like the automotive industry, aerospace, or heating, ventilating, and air conditioning. There are several industries where motor drives are used. So there is always a need for changing the speed of the motor. And that in turn drives the basic block diagram that we saw earlier and the need for having adjustable speed. So before electric drives were available, mostly it was all mechanical means to control the flow of fluids, gases, liquids in various applications, in industrial applications, at home. And using these mechanical means was not really the best way. It was inefficient in terms of wastage of energy and things like that. So that basically was the start for the development of electric drives. And of recent, the technical advancements in power electronics as well as microelectronics, are basically chips which are available to basically go into the heart of the uh, electric drive, which can be both power electronics as well as the uh, microcontrollers in the controller. So advancements in these fields have enabled a really huge strides in electric drives. So as a result, of course, controllers have also improved. The power electronic devices have become capable of handling higher voltages, higher currents, and much faster switching capabilities. So typically the power electronic devices, which are in the power processing unit. So we have typically IGBTs, power MOSFETs. These are the devices that are currently in use. So the industries that we discussed earlier, where they need adjustable speed drives. So the benefits that they derive by having adjustable speed drives, they have a very good control system. So they will be able to precisely control the speed of the motor or the position of a mechanical load. the efficiency is much higher, which was a problem with earlier mechanical based systems. And typically, electric drives require less maintenance because there are less, joints and issues with hydraulics or pneumatics or issues with friction and things like that. So the maintenance cost is lesser. So it's much cheaper for all these industries to make use of electric drives. As the technology has advanced and electric drives have become more and more capable in terms of the amount of power they are able to deliver. So, ranging from just a few kilowatts to megawatts of capability. So, that has expanded the application of electric drives in various industries. So, if we go deeper into the applications of electric drives, I'm sure everyone here is aware of the most common application today is with electric vehicles, where the IC engine is now replaced with the complete set of electric drive, electric motor, and then powered by a battery. So of course, electric vehicle is the biggest one of the biggest industries where electric drives have become so important now. But there are of course other areas in various other industries. So let's see what those other industries are also. So the first picture, of course, is Tesla, which is I think the most well-known brand of electric cars. So beyond automotive, so we see application in aerospace, where aerospace is also moving towards, or already they are having some steps where they are going towards more electric aircraft instead of the regular, pneumatic based or hydraulic based movement of the surfaces in an aircraft. So many of the flight control systems, actuation, all of this today are driven with electric drives. So we'll look at a case study later when we examine one case study from aerospace. Beyond this, we have the oil and natural gas industry, the movement of cranes, conveyor belts, hoists. All of these are significant applications of electric drives. And generally for industrial automation, process industry, maybe it's like the cement industry and things like that. So there again, electric drives have similar applications. Industrial robotics, which also is part of the automotive domain, also has significant application for electric drives. Steel mills and most of the other metal processing industries, they use a lot of grinding applications, milling applications. So all of these are basically use electric drives. The transportation industry, locomotives, and most of the high-speed electric trains that we have are all based on electric drives. And coming to home appliances, which most of you are familiar with, basically the refrigeration, washing machine, air conditioning, all of this use electric drives, basically with motors of different power ratings. So if you look at the application, it is so vast that it touches some aspect of our lives daily. So that is the extent to which electric drives have pervaded our daily life. So yeah, this is just summary of what are all the applications that we typically come across. So like I mentioned, for the process industry and heating, ventilating, and air conditioning, steel industry, transportation, in buildings with elevators and escalators, industrial automation, automotive, of course, textile industry, fast moving consumer goods for basic production and running the conveyor belts, in aerospace domain, as I already spoke about that. oil and natural gas, and home appliances. So it's really a vast application that is there for electric drives. Let's look at what goes into building an electric drive. So for any application, the first step is basically the requirements which are provided in terms of what exactly is the load that has to be driven, and more importantly, what should be the load profile. So the load profile, it can be like a linear movement. It can be just a direct rotational movement. It can be a start-stop type of motion. It can be continuous operation. It could also be variations in speed, which has to be controlled over time. So this load profile is a very, very important requirement which has to be considered at the start of building an electric drive. Once we have clarity on the requirement, the selection of the motor based on the application requirements uh, is it's typically driven by what sort of torque, speed, characteristics we require, and what sort of a load it is handling. Modern day, we typically tend to use BLDC motors or permanent magnet synchronous motors and induction motors. So the motor selection also has to go hand in hand while the drive is being built. Once the selection of the motor has been done, the system level design and modeling. So basically, it is the figure that we discussed earlier, how the power processing unit is interacting with the motor and the sensor and the controller, all of these. So how they come together. So that if it's visualized as a control system, so that control system has to be designed and modeled, verify that it is going to give the performance that is expected of by the what is provided by the requirements. So once this modeling is done, it is in the virtual environment. So now we need to translate it into realizing practically the hardware. So that would the requirements basically get translated then from a system level to hardware and software requirements. So the hardware requirements basically drive the hardware design and development. So this would go into both the power processing unit, which is the power electronics part, and also the controller, which involves analog and digital design. So the hardware design output would basically be a PCB boards, and for power electronics, it could be PCB mounted. It could be parts which are directly mounted inside a mechanical chassis. Okay, so as I mentioned about the chassis, so mechanical packaging or basically the box to house the power processing unit and the controller is coming into the packaging format. So you need to have a good form factor for the motor drive that is designed. And in parallel to the hardware development, the software or firmware development, which is basically the intelligence which is going into the controller to control the different algorithms to control the motor speed and position of the load and all that. So that happens in parallel with the hardware development. And as they develop various functionalities within the electric drive, there will be module level testing for each of the functions of the electric drive before bringing together the whole all of the components and then integrating the electric drive. So once integrated, normally the drive will be put into the system where it is expected to perform the function. So maybe it is used for electric vehicle. So it should be basically, testing out with driving the car essentially. Or if it is used for aerospace applications, it would be to say move a particular surface in the aircraft. Then it would be carried out at a system level where we actually move the surface of the wing or different parts of the aircraft. So that's a system level testing where the function, the performance, and the critical thing being qualification testing. So qualification is for each industry there are certain standards that have to be met. So you have to test and qualify the product that they meet all those standards. So once the product has now gone through the design and testing steps, the critical part is basically the production ramp up, so that when volumes pick up, the you're able to basically assemble and supply these drives. And also the lifespan of electric drives, as I said, there's less maintenance required, so they tend to last quite a long time. So the aftermarket support after you have sold the electric drive for various various applications, that support will have to be provided for quite a long time for any addressing any field failures and things like that which can come up. So the other thing, of course, is the predictive maintenance. So data analytics is ever pervading. It gets into all the aspects of every industry. So the maintenance and analytics that would be used to diagnose if there is any fault that is likely to occur, or if there is some performance issue with the drive. So this sort of a predictive maintenance is also one of the key factors that is coming into the electric drives of recent.